Hi, this video lecture has two parts. The first video lecture covers up to page 9. I recommend you to watch this part 1 first. Before explaining the probability distribution, let's learn about the probability. Probability is written as P, small p or in large P, in statistics. It is the possibility of an occurrence. Let's try to answer to the following two quizzes. What about the first question? When you throw a die, the possibility of having any of these 6 numbers should be equally 1 over 6. It's an easy question. Then now you have 3 dice and you throw them at once. What is the possibility of having total number of 3 or 4 or 17 or 18? The probability of having the total number of 3 or 18 is actually the 3 times of 1 over 6. So you multiply 1 over 6 3 times, which will result 1 over 216. What if you draw a histogram about this result? So on x-axis is total number, so 3 to 18, and in y-axis the probability. For having 3 or 18 is the rarest case, so the probability will be the lowest, which is 1 over 216. And here equally at this height. But already when you assume that you have a total number of 4, there are more possibilities to have the total number of 4. So 1, 1, 3, or 1, 3, 1, or 3, 1, 1. So already to have a total number of 4, you have 3 times higher probability, right? So here corresponds to 3 over 216. So in this way, you can accumulate the frequency and it will appear somehow in this shape. That's what you can easily guess. And before you draw this curved line, because on x-axis there are only 16 categories, so you draw a bar chart which has a height of the probability in such a way. And here, so this is actually histogram. Histogram is the actual shape of the distribution for each group. In this case, each total. Now let's think about this situation. You spin a top. What is the probability of its indicating exactly at 30 degrees? The exact 30 degree is a point, but that must exist only conceptually. There is no such physical place that points very exactly the 30 degrees. Instead, we can calculate the probability of the tops indicating between 30 and 60 degrees. The stopping degree will be within 360 degrees. Therefore, the probability between 30 degree and the 60 degree, so here is 30 degree approximately, is the probability that a stops at within this angle is 30 over 360 degrees. That's the actual probability we can calculate. So it would be 1 over 12. can we draw a distribution of the probability in this case? In x-axis is a degree, and y-axis probability. And because this top looks symmetrical, so the probability will be equal. Theoretically, it's equal. And 360. The size of this area will be 1, right? 1 means 100% in percentage unit. So in this case, the probability is continuous, right? So the probability is continuous. Different shape from previous page, but it's a continuous. Let's compare the histogram and the probability density function, which are continuous. In histogram, the probability value is the ratio of a bar or bars to the total size. Therefore, the probability of having higher score than 80 is actually the summation of these 3 bars, the ratio of the summation of these 3 bars to the entire ratio of all these gray bars, including these 3. That's actually the ratio, right? If we only look at the histogram data. Now, in Excel or in SPSS, the trend line drawing, or these softwares offer a trend line like this. And this trend line shows you the distribution of the data, supposing that when you have a population. In SPSS, you can test whether the distribution of the histogram in these gray bars, histogram looks like a certain distribution type. Typically, we test the normality of the distribution. The exam score in 2011, it is displayed here as a histogram. Each range of the score has different frequencies. Based on this histogram, a trend line is overlapped. And I think it seems that the distribution is still acceptable as a normal distribution. In distribution probability density function, the probability value indicates the integrated area. So the shaded area here. Therefore, the probability of having a higher score than 80 here, you calculate actually the area size of this area. Okay. In statistics, we always refer to a certain probability density functions, and they are continuous. As said before, the probability value indicates the integrated area in distribution of probability density function. For the statistic techniques we as design researchers are mainly using are within the following distributions. They are normal distribution, t-distribution, f-distribution, chi-square distribution. The chi here looks like x, but it's a Greek letter chi, and this is the chi you publish your paper, right? And in fact, there are many different distributions. Let me show you. Yeah, so here you can watch many different distributions, and among these, what we typically use are fortunately limited to these 4. Okay. And now we look into what normal distribution is. The normal distribution looks symmetrical and bell-shaped, inverse bell-shaped. It is called also as Gaussian curve. In a formula, the normal distribution is formed in this way. Of course, you don't need to memorize this. But if you draw the function based on this mathematical formula, then this will appear. The dark blue is less than 1 standard deviation here, within here. Sigma is a standard deviation we learned. And when the data are within plus minus 1 sigma, then the data set account for about 68, this plus this, 68% of the set, whereas 2 standard deviations, so from here to here, so you add this, and this accounts for approximately 95%, and 3 standard deviation almost account for 99.7%. Based on this, some companies have a strategy of a 6 sigma, and well, 6 and sigma look same, but very similar, but it's due to my poor writing skill. So number 6 and sigma. So when the error ratio is beyond 6 sigma range, then usually when a company produces a product, almost 99.7% of the product are correct, or they are not defect. So it's almost perfect. So pursuing that perfection, companies try to make their strategy like a 6 sigma. And in going back to the normal distribution, in normal distribution, when set value, so this x-axis is called as a set value. Z value either exceeds 1.96, so 1.96, 1 minus 1.96. If we cover here, then the size between here and here, so this area is exactly 95%. And 95% is very relevant in design studies, that Z value, which corresponds to the 0.95, is 1.96 minus here and plus here, 1.96. Okay. And all inferential statistics assume that the distribution of scores or data on the dependent variable fits to normal, and the normality can be statistically assessed. Let me show you how to test it, and let's test whether the exam score of last year, 2013, fits to the normal distribution. We have a data here. So this was the exam score in 2013, and I'm gonna copy this file to SPS software, and variable is exam, right? Okay, and analysis, non-parametric statistic, and here one sample, the KS test, and I bring here, and I would like test whether this score distribution is fitting to the normal distribution. Okay, so our focus is usually 95%, and here it results provides that 0.660, so it's far larger than 0.05. So it's not different from the normal distribution. That's actually what it is saying. We are going to learn more about reading this kind of data from next week. And actually we can draw a histogram of the score. Well, it doesn't seems to be very much normal distribution, but statistically it is normal distribution. And let me draw a line. So this line is normal distribution. The curve fits to normal distribution, and the histogram doesn't really support this shape, but statistically it is not different from this curve. That's what this data is saying. Okay, so you don't need to worry about whether your data are fitting to normal distribution. This kind of normality tests are very robust to quite poor data. So usually we can easily assume that our scores we collect or our data we collect are fitting to the normal distribution. Okay, let's go back to the slides. Okay, here you have four curves, and all four curves are symmetrical and bell-shaped. Therefore, all curves are fitting to normal distribution. But in particular, when the mean value, so mu is 0, and the variance, so sigma square value is 1, then it is called as standard normal distribution. Among these four curves, the red one is the standard normal distribution. We can transform the data in the scale of the standard normal distribution. We call this process as normalization or standardization. When we have measured the same thing using different scales, like if you have measured same thing with a 7-point scale or 9-point scale and you want to compare the scores, because you have different scales, actually it's impossible to match 1-to-1, right? That in such a case, you can normalize both data and then you can compare 1-to-1. Okay, let me explain you more about this normalization. When the data are standardized, the calculation is being based on the normal distribution and indicate how many units any given value is above or below the mean of the distribution. When you transform a set of scores to the corresponding z-scores, the resulting distribution, by definition, has mean of 0 and standard deviation of 1. So the initial x-axis had a range like that, and when you convert the scores into z-scores, when you transform the data into z-scores, which means you convert every single score and you subtract it from the mean of the scores, and you divide this subtraction through standard deviation, then that will be a z-score. So if you compare the shape of a histogram, they should be similar. Let me show you how to transform the exam score into z-score. In Excel you can do it, and of course in SPS you also can do it. So let's do it in Excel first. Here, z-score function, standardize this x, and mean is average of here, and standard deviation here should be 18, yeah, and standard deviation Example. So the test score of the first person is converted to like that. And in XPSS analysis, descriptive statistic, and here you save the standardized value or test score as additional variable. You go back to the sheet and here, okay, this is identical with this. So quickly you can do it. I think you are now meanwhile acquainted with these curves. As an additional information, you need to be aware of one-tailed or two-tailed. Two-tailed. The size of a shaded area is the probability here. So the P equals to 0.05 here means the size of this shaded area is 0.05. In one-tailed situation, the shaded area is either in right tail or in left tail. In two-tailed situation, the shaded area are symmetrically positioned on left and right. Therefore, the size of each shaded area is actually and equally 0.025. And here as well, therefore eventually the size reaches to 0.05. Whether one-tailed or two-tailed are relevant, it's actually relevant when you perform the t-test. We will cover this issue again when we learn the t-test. Then it is much more clear what these sentences are actually meaning. That two-tailed test is more for a more scientific and stringent study, while one-tailed test is for an explorative study. So it offers a more generous decision. Okay. So this is the first part of the video lecture. See you soon. Bye.